Before I proceed any further, can I assume that this is clear? Right? Fine. Okay. So, what are the observations that we make? The observations are that a compiler bridges the gap between a source program and a target program. Compilation involves gradual lowering of levels of the IR. IR stands for intermediate representation. Which intermediate representation that we have seen? We have seen the sequence of tokens, we have seen parse tree, we have seen abstract syntax tree, we have seen tree address code, we have seen register transfer language, and we have seen assembly. And these are the different IRs that we have seen. Okay. In each IR, as you can see from this picture, there is a gradual lowering of the level of abstraction. This is very abstract, okay, and this is most concise, the smallest representation. Then we add some more details. What are the details that we add? In the parse tree, we add the details about how these things are to be grouped. So this parse tree tells us the structure. So here in the first statement, the structure is implicit. Here the structure is implicit. Parse tree explicates the structure. It says, okay, this is an assignment statement. It has three parts, right? So when we write the program, we have that structure implicitly in our mind. Parse tree explicates it. So we have added more details. When we go to abstract syntax tree, of course, we throw away some details that we do not need, but add more details. What details do we add? The names of the symbols, their types, right? Then we go to tree address code. Which detail have we added in tree address code, which is not there in abstract syntax tree? Yeah. Sequence of operations. In abstract syntax tree, the sequence is implicit. It's assumed that we know how to read the abstract syntax tree. But here we are making sequencing, the control flow explicit. When we go from tag list to RTL list, have we added the actual machine instructions, right? And when we go from RTL to assembly, we added the stack offsets, we added the actual registers. So compilation is essentially a task of gradual lowering of the levels of IR of an input program. That's the meaning of the second bullet that we have. Every time you write a compiler, this is precisely what you have to do. And GCC does this in 357 steps. Right? There are several steps. Many of these steps do not lower the level of the IR. They keep the same IR but change the IR. So either you can get abstract syntax tree to tree address code to RTL, or you might say I have tree address code and I'll analyze it and optimize it. What kind of optimizations we can do? So we will see some examples tomorrow. I may want to replace some variables by constants. I may want to say that some expressions are not required. So there are two ways this can happen. Compilation can happen. Either you take an IR, lower it to the next IR, or you take an IR and optimize it, give the same IR but more optimized IR. So in most of the passes that GCC does, most of them are optimization passes. The IRs, the lowering of level is not that detailed. So the first IR is what is called abstract syntax tree, then we have generic representation, then we have GIMPL representation, then we have RTL representation. After GIMPL, we have control flow graph, then we have SSA, then we have RTL, and then we have machine code. So levels are only 7 or 8 within GCC. But at each level, it performs lots of optimizations. Right? That's how a typical compiler works. Okay. The design of IR is the most critical part of a compiler design. How many IRs should we have? What are the details that each IR captures? For example, GCC initially did not have a tree address code. GCC initially started from ASP and directly started generating RTL. That put some limitations. Then GCC designed something called is trying to do optimization of JavaScript script programs. How many of you have used JavaScript? Several of you. So you would know in JavaScript, things can change dynamically, types can change dynamically, you can generate code dynamically. How do you compile it before execution? That's a big challenge. Compilation is still easy. How do you optimize it? So that's the PhD. That's the question that PhD is asking. How do I compile it? And what is the critical insight there? The critical insight is the student called Nitesh, who will be a TA here when Professor Manas comes. You can ask him, this is his PhD problem. So what he does is he has come up with a very good intermediate representation. He calls it iridium system, where he has carefully designed the features that are required to represent a dynamic language such as JavaScript. It could be TypeScript, it could be Python. So he's trying to design it in a language independent way. His biggest contribution is a set of minimal insights, clean insights that gives a good IR. And once you have good IR, you can do lots of things. So he is able to do lots of optimizations of JavaScript programs which no compiler at this stage can do. Right? So therefore, intermediate representation is the most crucial aspect of a compiler. Unfortunately, no book emphasizes it. Books tend to take it for granted. But practically, when we work on compilers, that becomes the most important part of a compiler. Okay. The other important requirement of a compiler is practical compilers are designed to be retargetable. What do you mean by retargetable? Retargetable means, let's say I have a compiler that generates code for PowerPC. Maybe I want it to generate code for 3x6. Maybe I want it to generate code for MIPS. So do I have to rewrite the entire compiler? That's highly undesirable. It would be nice to keep as much thing as same as possible and change only the part that is directly influenced by the target machine. So we should be able to retarget, change the target of a compiler. Okay. So the idea here is that we talked about front end, we talked about back end. Front end is something that's dependent on the language. Back end is something that's dependent on the machine. So if you want to change the machine, you should be able to generate a new backend, ideally from a specification. Instead of writing C or C++ code to generate code for that particular target, it should be possible for. So, what kind of a specification it could be? The specification could be the registers, the addressing modes, different instructions, structures of the instructions, etc. So we could specify these details, and eventually we can give the structure of the final output that we want, and then we can have a tool which takes this input and generates a backend. This is highly desirable. Most practical compilers try to do it, but this is one of the most difficult problems in compilers. GCC, for example, requires you to write the specifications to generate code, but turns out that for x86 machines, the specification runs in, hold your breath, 80,000 lines. From that, C code is generated, which generates the compiler. That tells you the enormity of doing real compilation. Okay. So now it's a very important question. We need to answer this question. Why is compiler construction a relevant course? And one of the questions that people often ask is, compilers exist for all languages. What is it that compiler writers do anyway? Why do we even need to study compilers? Compilers exist. This question is something that I hate. The reason why I hate is not because asking this question is wrong. The reason why I hate this is that it creates an existential crisis for me. Why do I exist? If compilers exist, then what the hell am I doing? getting requests from my students who are in charge of compilers in different companies, and then they say, please suggest names of the students who we can induct in our team. In fact, at IIT Bombay, we started a new event called Placid, which stands for PL and Compilers Day in the industry. Because my friends and students keep asking for names, so what I did was I said, you come to the IIT and talk to my students. So now we have this event where companies like IBM, Microsoft, Qualcomm, Quadric, AMD, all these companies come, and NVIDIA, and then they tell the students what is it that they're doing in the compiler field, and then students can join those companies. So there's a lot of work happening. But very few people are required, but that is still in a short supply. But the reason why this remains an important point is that translation and interpretation are fundamental concepts in computer science. Computer science is all about building abstractions on the reality. So you have to build an abstraction of the reality, read that abstraction, and perform some task. That is at an abstract level, just like compilation. So in the break, someone was asking me a question about LaTeX. I don't know how many of you use LaTeX. It takes a specification and it generates a page, that's a PDF page. That's also compilation. Okay? So the principles are universal. Okay? So computer science is all about building layers of abstractions and bridging the gaps between successive layers. So you have highest level of abstraction and you have lowest level of machine. How do I bridge this gap? Compiler construction is the only course that teaches you how to bridge this gap from high level to the low level. Most other courses either focus on this part or that part, but not the entire spectrum. It's the compiler construction course which covers the entire spectrum and exposes you to how beautiful abstractions can be built. I mean, GCC, for example, is an artifact which shows that. So there are so many abstraction layers. That's why it uses 357 passes. Okay. And the most important reason why I tell my students they should study compilers is knowing compiler internal makes you a much better programmer. You understand what's happening behind the scene. Somebody has written the statement. You can visualize, okay, what would be its syntax, what would be its semantics, how different parts work with each other, how is it going to execute on the machine, and that helps you to debug your programs much faster. When there's an error, either runtime error or a compilation error, you can imagine what could have gone wrong because you know the internals. So even if you don't have to actually write a compiler in your life, you still become a much, much better programmer when you understand the compiler internals. And the tagline that often I give to my students is, we write programs that write programs. Everyone writes programs that read some numbers or some data and produces some result. We write programs that read programs and generate programs. So we are raising the level of abstraction to a higher level. Okay? And the beauty of and enormity of compiler essentially lies in raising the level of abstraction and bridging the gap. Not just bridging the gap without performance penalties, and this is where entire challenge comes in. I don't want performance penalty. I want performance. I want to be able to run that program as fast as possible. I want to allow the user to write a program without too many details. As a compiler writer, my compiler will supply those details to ensure that we get the best performance possible. In fact, most of the work that my students are doing are how to analyze the program to achieve performance. We'll talk about program analysis tomorrow, but the idea is to read a program, analyze it, and see what is redundant, what is it that can be done better, how can I optimize my program better. Okay, so this is the most beautiful part of it. You have a big abstraction gap and you have to create layers and ensure that when I go from this to this, there is no performance penalty. There is a performance gain that I go from one layer to the other. And the other challenge is you have to meet the expectations of users with a wide variety of needs. Okay, so where can I use lessons learned in compiler design? So compilers for all languages exist. So what can I do with the technology? Well, I'm not going to go into the details of this talk. You can can see this as a sales talk. I'm just trying to say you the point that this is a useful thing. You can use it at multiple places. Let me not do the hard sell. You can see for yourself that it's useful at many places. Okay. So, so the other aspect of compiler is developing and maintaining a rather large code base of millions of lines. JCC runs in more than 30 million lines. How do you walk the maze of such a large code base and make meaningful changes, meaningful updates? You become a much better programmer when you start dealing with large programs like this. Okay? And compilers make extensive use of tools to generate modules from declarative specifications. So we have higher level, for example, scanners are generated from specifications, parsers are generated from specifications, even semantic analyzers can be generated from specifications, backends can be generated from specifications. Unfortunately, optimizers are not generated from specifications. That's one of the gaps. We will see why that may not be so easy to do it to get the best performance. Why does it have to be written mostly manually? Okay. The important thing is we have to handle every possible program from an infinite set of possible programs. You know, if I am doing a classification problem, if I am doing machine learning, I can say, oh, I can handle 90% inputs correctly. You can't write a compiler that compiles 90% programs correctly. It has to compile every program correctly. Even if you say it miscompiles 1%, you're talking about 1,000 lines. It means that 10 lines are compiled wrongly. Talking about 10,000 lines, even 100 lines are compiled wrongly. Talking about 1 million lines, Firefox is, for example, 40 million lines. If you say just 0.1% error, just imagine what is the size of the error in a 40 million lines. Compilers cannot tolerate this. Okay, compilers have to be correct all the time. Sometimes errors creep in compilers because of optimizations for performance, not for correctness. Okay, so compilers have to exploit advanced features of rich computer architecture. So now we have out of order execution. How do we compile a program when the target machine is going to do something else altogether? We will perhaps only talk about modern challenges. We will take some examples of this. Okay, so the whole idea is the beauty of an enormity of compiler lies in spanning both theory and practice and everything in between. You can't say theory and practice and they're disconnected. You have to connect theory to practice and practice to theory. So you have to span everything in between, okay, rather deeply. It's not something trivial. So it essentially involves translating deep theory into general, efficient, and scalable practice. And that's what the beauty of compiler construction as a field lies in. Okay. So it uses principles and techniques from many areas of computer science. Let me not go into too many details here. For example, in theory of algorithms, you have to study mathematical logic, lattice theory, linear algebra, probability theory, greedy algorithms, heuristic search, graph algorithms, dynamic programming. So all fixed point computations, finite automata, pushdown automata, all these concepts come into play when you actually work on compilers. When you talk about data structures, you have to understand sparse representations, sparse scanner parser tables, different kinds of data structures, graphs, DAGs, etc. So this is essentially, these are the aspects that make compiler construction a very beautiful topic. Okay, so let's move on and look at compilation models. But before I begin with that, I would like to pause here and take any questions. Any observation, any curiosity? Of course, lots of things that I have said are absolutely high-level details. Many of you may not be able to relate to them right now, but that's okay. Yeah. Yes. So the critical insight is to see that this is a computation that has been given, and I have to find out what is the best was the most efficient way of implementing that computation on my machine. Okay, so I can tell you a bit of story. First compiler was written around 1954 by John Backus and his team in Bell Laboratories. Not in Bell Laboratories. I think it was at IBM. Okay, so they wrote that compiler. What is the critical observation that they made? So at that time, high-level language didn't exist. Okay, people used to do programming in assembly language, and there were people who tried to give high-level specification and generate code, but they're not very successful. Why? Because they could not handle that performance penalty part of it. So the observation they made was that the translation of the loops done by those high-level systems was not very efficient. Then they studied what is the way in which loops can be translated most efficiently on the IBM 704 or whatever that machine was. Okay, they tried to do that, and then they studied, okay, I can use what at that time were called as index registers, and I can use that to run the code efficiently. Then they said, okay, now here is the input and here is the output. This is the input containing loops and this is the output, the most efficient way of executing this input. How do I bridge this gap? Then they try to imagine, okay, from here I can go here, from here I can go here. So the whole idea, the way it works is, first of all, a good optimizer writer first has to know what would a machine do, what can a machine do efficiently. And then the writer has to imagine what is the user specifying. And the writer has to build this bridge between what the user is going to write and what machine can do better. So the writer has to, compiler writer or the optimizer writer has to develop theory of all these concepts of, okay, here is a specification and this is what I want to translate into it. So I can go in maybe 3 steps, 5 steps, 10 steps, maybe 100 steps from here to there. That is how we try to ensure that there are no performance penalty, and that's what makes a compiler a very beautiful topic. Yeah. Any other question? We'll look at some of these examples later when we talk about modern challenges. Yeah, please go ahead. There are two hands. Yeah. Okay. Good question. The question is, how do we avoid performance penalty? If we have more IRs, aren't we doing more work? Are we not giving more performance penalty? That's the question that is being asked, right? I mean, if you have a hello world program, you have to go with 357 steps. Isn't that a performance penalty? That's the question that's being asked. Would anyone like to hazard a guess as to why this objection is valid or why this is not valid? At an abstract level, this objection is very valid, but it brings us to a very core insight of compilers, which I want to bring up. But I want to hear from you. What do you think about? Yeah. But if you have more steps, won't you need more time? But if you have to jump for 1 meter 100 times, like 0.4 multiplied by 100. Yes. Yeah. have to distinguish between compilation time and execution time. You may take more compilation time. You can afford to take more compilation time, but that makes the execution of the program faster. There are two distinct times that we're talking about. Compilation time versus execution time. Our goal is to optimize the execution time. Even if compilation time takes a little more time, that's okay. Of course, that is also not very okay because practical algorithm, if your compiler starts using cubic algorithms, the compiler people hate it. Anything more than linear is something that compiler writers don't like it. You go to a theoretician and say, oh, I have a polynomial algorithm, I made this great success. Polynomial. We don't want anything more than linear. Even quadratic is something very bad. That's where the algorithms come in. So the idea is not only to have efficient algorithms, but the idea is to worry about the efficiency of what these algorithms produce. Right? I mean, for example, if you want to combine GCC source on this laptop, it might take maybe half an hour to build GCC. Half an hour of compilation, you're talking about 30 million lines. Right? Once you compile it, it runs very fast. Okay, but fast compilation is also one of the most important considerations, particularly when we are doing JIT compilation, just-in-time compilation, because we are compiling during execution. So you will have Professor Manas Thakur coming in and teaching you from 15th onwards. He has done a lot of work on JIT compilation. Good. There's one more hand. Yeah. Very good question. The question is, can we go from lower level of abstraction to higher level abstraction? Would anyone like to guess? Yes. And good. But why would this be interesting, by the way? Why should this be interesting? Reverse engineering. Yes. So yes, there are tools that take a lower level abstraction, which we don't understand, and then give us a higher level abstraction that we understand. This problem is much more challenging. Simple reason, this is much more challenging because there is a lot of research. This area is called decompilation. There's a lot of research in this area. I'll give you one simple example of a challenge. Okay, so often practical machines have a jump instruction on a value in a register. Right? So depending upon the value, so we PC relative, the various kinds of addressing modes. So I have a value in a register. Does it represent an address in the memory or does it represent a value to be computed? So if I have jump relative to the value in the register, how do I generate a control flow graph? How do I know that the control flow is going to this statement and not that statement and not that statement? With the value decided at runtime. So how do I know that? So that's one of the challenges. So there are many interesting challenges. So there is a lot of work being done in decompilation, which has its own use cases and its own challenges. But a much bigger chunk of work is done in actually forward compilation. One of the reasons why decompilation is done is that they want binary compatibility. So you have some changes in the processor detail. You want to make sure that your binary runs on the new processor as well. Maybe you added some more instructions, you changed some things. So there could be binary to binary translation, in which they have to perform analysis of the binary and synthesize the next binary. So that has again some element of decompilation in it. I'm glad the kind of question that you are asking. I'm glad with the kind of question that you are asking. Please keep asking more questions. Yeah, anything else? Shall we proceed with compilation models? Okay. So how does a typical front end works like? So in most cases, what happens is the parser is the driver routine of a typical front end. Something, what does a parser do? We will see more details later. Derives essentially the So whenever a parser requires the next token, parser accumulates the tokens that it has seen, the parse tree that it has seen, and it knows that now I can't proceed until I know what the next token is. Then it calls the scanner internally. And the scanner reads the source program. So parser does not read the source program. Source program is always read by a scanner. And scanner sees it as a sequence of characters, and the sequence of characters has to be converted into a sequence of tokens, but the sequence of tokens is constructed on a need basis. Whenever the parser says, give me the next token, the parser will, in parser code will invoke the scanner which will read the next. So the scanner will maintain a file pointer. Scanner will maintain a pointer in its data structure saying, I am read up to this. And when the parser says, give me next token, the scanner will read from there onwards until it finds the right sequence and return a token. So you can see there is this both way flow. There is this call from parser to a scanner. Parser reads the source program and returns the next token. Once the parser has identified a structure that it recognizes as a sufficiently independent structure, this structure could be an expression, this structure could be an assignment statement, this structure could be a while loop, this structure could be a compound statement. So once a parser identifies that structure, it it calls semantic analyzer. So parser internally says, okay, now I have seen an expression. Hey, semantic analyzer, tell me the semantics of this. Tell me whether this is semantically valid. Am I adding a number to a string? That's something that parser doesn't know. Semantic analyzer knows. So semantic analyzer says, okay, let me check whether this is semantically valid. And the semantic analyzer will say, okay, it is semantically valid. If it is semantically valid, it will produce, it will return an AST as a data structure to the parser, and the parser will emit AST or linear representation, 3 address code plus symbol table. So this is how a typical front end works, and in order for it to work, it internally uses a symbol table handler. So a symbol table handler is accessed by a scanner. For example, when a scanner sees a variable name, the scanner will insert that variable name, install that variable name in a symbol table and return a pointer to that variable to the parser, so that parser knows which variable we are talking about. And the semantic analyzer will access that pointer and go to the appropriate entry in the symbol table to extract the type of the variable and will say, okay, here actually I am expecting an integer, but you are giving me a string. Sorry, it's not allowed. That's how semantic analyzer will give you an error. If it finds that it has the right variable, so if there is an error, there is this error handler and the various strategies of handling errors. One of the strategies is, as soon as you see an error, you abort the compilation, which is what we do when students write compilers. The practical compilers are not supposed to stop at the first error. The practical compilers should somehow recover from the errors and flag as many errors as possible so that the users can fix, because many of these errors may be independent, some of these errors could also be dependent. A very important research topic in the compilers is how do we handle errors. If you want to understand it, write a C++ program and make an error in writing the classes. And then you will get 1000 lines of errors. And then you will not know where the problem is. So what is the minimal error reporting that a compiler can do? How can a compiler give a good diagnostics to a programmer so that the programmer can focus, okay, I need to look at this. That itself is a big research area. Error handling is something very involved, very interesting, very challenging, and a mature area of research. And still a lot of work needs to be done. So this is how a typical front end works. Okay, the output of the front end is an abstract syntax tree or a linear IR. Right? So let me show you the linear IRs. I didn't show you the linear IR because I didn't have SCLP. Oh, I had SCLP running, but where am I? Yeah. So assignment resources. So I can check. Oh no, this is not the directory I want to be in. let's just run dot slash L5 SCLT minus D minus show. You see AST, let's see show tag, and now we will say minus stop after 3 underscore generation, and we say level 5 L5 exmp1 dot c. Okay, so this it gives us a 3 underscore. Okay, we can take perhaps more interesting example. I don't know which one it is. So here it is generating this 3 underscore. Okay, so you have temp equal to is called to the function with some parameters on this. So you can examine 3 underscore. You can say okay, let me say show RTL, and you say show RTL, and it shows this is RTL that it is generated. It has generated. Okay. Unfortunately, the TS told me that there is a difficulty in running this SCLT executable in their laptops because there is some problem with libstd something C++ library version of the library is not the version that there on my laptop. So unfortunately, although I have given you this code, you may not be able to run it. But the whole idea is that you can see various things. So you can say, for example, show AST, and it gives you an abstract syntax tree, right? Okay, so that's it. Let's get back to what we were talking about. Yeah, yeah. Before I proceed any further, any questions? We are going to look at some more details on this, some more details on this, and some more details on this today. But not the full details because the actual algorithms are doing this is beyond the scope of this winter school. Before I proceed, then there are many other ways of organizing the front end. One way would be that actually you run only the scanner, produce a sequence of tokens, and then you run a parser, you emit a parse tree. So it can be completely sequential. That's how it used to be. When the first Fortran compiler was written, the memory wasn't large enough to keep the entire compiler in the memory. So they would just generate a sequence of tokens, store it on a magnetic drum, that was the secondary memory, and then the next phase would once again the code of the phase will be loaded, the sequence of tokens will be loaded, and parse tree will be constructed. There are many ways of doing it, but this is how practically all compilers do it these days. Right, that's the front end. Let's look at typical backends. So as I said, so this is machine independent intermediate representation, and this is a machine independent optimizer. Here it doesn't change the level. The level of the IR is still same. So you're reading an IR in one language and you're producing a program in the same language, but in the process, what are you doing? You're looking at what are the evaluation that can be done at compile time. You're looking at how to eliminate redundant computations. Okay, so these are the examples of a very broad category of optimization. Most optimizations fall in one of these two categories. Once you have done this optimization, then you have a code generator. So code generator takes a machine independent intermediate representation and produces a machine dependent intermediate representation. Now here the level of IR is changing. And what kind of things it can do? It can select the right instructions, it can perform local register allocation, what is the best use of the registers, it can decide in which order a parse tree, which order it is. So let's say you have an AST which is plus followed by an expression A1 followed by an expression A2. Once you have this AST, is it necessary for you to generate code for A1 first? Can you or A2 first? Does it have to be generated in the same order? What do you think? You have a plus, expression 1, expression 2. Should I necessarily generate the code of expression 1 first? What is your guess? Either can be done. Why can it be done either way? We are saying plus is commutative. So let's replace plus by minus. So I have expression 1 minus expression 2. Should the code of expression 1 precede the expression 2? What do you think? Minus not completely. Yes, so you can generate the code in any order, but when you perform the minus operation, the result of the first expression, so you can do expression 2, store the value in T1, you can do expression 1, store the value in T2, and then you can do T2 minus T1. That order is important. For which tree do you generate the code first is not important. Now, why is this an interesting detail? This is an interesting detail because the order in which you generate the code can help you minimize the number of registers. There's a beautiful algorithm called schedule numbering, labeling, which says that compute the hard subtree first. So subtree which requires a larger number of registers is evaluated first, and then we evaluate the smaller subtree. Now, let's say this subtree requires k registers and this subtree requires k minus 2 registers. So once you have evaluated this subtree using k registers, the result will be stored in only one register. So you are guaranteed that you have k minus 2 registers available for this subtree. You do not need an additional register. You can minimize the number of registers. So these are the kind of choices that a code generator would make. I admit that this detail is very abstract for you to see, but a typical strong compiler course will teach you why this matters. And if you're curious, I'll be happy to show you examples where it matters. We can take it offline. Okay, so that's how we generate the code, and then we have a machine dependent optimizer. So we have machine independent optimizer, which didn't worry about the machine details, looked at only the semantics of the program, and now we go to semantics of how they can be implemented on a machine. Here we worry about global register allocation. We do what is called people optimization. So people optimization is exactly what the name suggests. You create a small window of 3-4 instructions on the code and see whether these instructions can be combined. So generation from abstract level to lower level, it exposes many redundancies. It's not very uncommon to have an instruction where I'm saying load a value in a register, store a value in a register, and load the value in some other register. Can I make the same register same? Can I make the two registers same? If yes, then I can eliminate load and store instruction. Or maybe I'm multiplying a number by 1, or maybe I'm adding a 0 to a number. So people optimization is one of the most powerful optimizations, and you can actually make the code much faster with that. And there are lots of PhD theses which have studied how to specify people optimizations at an abstract level and generate the best people optimizer. They use a word called super optimizer. A very interesting work has been done in that field. So we have a people optimization, then we have global register allocation. Global as in now I am connecting register allocation across the statements. So if I have the value of a variable a in register R1, should I keep the value in R1 all throughout the program, or should I store the value of a back and then load it when required? These decisions are taken by a global register allocation. So it finds out candidates that deserve to be given register. We will see a very interesting analysis tomorrow called live variables analysis, which essentially tells us which are the variables whose values are read further. And these are the variables whose values should be kept in register. So live variables analysis feeds a register allocator. It tells that, look, these are important values that should preserve, and then register allocator decides, of these 2000 values, I have only 16 registers, I have 2000 values. So how do I select the registers properly? The most dominant algorithm for register allocation is what is called graph coloring. How many of you heard graph coloring problem? Graph coloring essentially says you have a graph and you have a set of nodes, and the adjacent nodes that have an edge between them should be given different colors. Why is that important? Natural example of that is you have a world map. And then there is instruction scheduling. I mean, if I know that, how many of you have heard of this term called pipeline in an architecture? So you know, so instructions have different stages. You have load, you have fetch, decode, execute, and write back. These are the minimum 4 stages. So while one instruction is executing, the architecture, the hardware part of fetching is free. So maybe you can fetch the next instruction, and then you can start executing the next instruction. Now you may have pipeline hazards. Value of this result is not ready. Maybe so you have A is equal to B plus C, and then you have something A plus something. So until this is written, even if you have fetched this instruction, you can't execute this instruction because you have to have the write back again, or at least have register forwarding. In which case, your architecture might insert a no-op between two instructions. How can I avoid no-op? How can I rearrange instructions so that I know the values are required when they are available? So this is instruction scheduling. One of the simplest algorithms for that is what is called structured pipelining. Again, the details are beyond our scope, but the idea is that you can rearrange instructions, maybe dovetail instructions like this, so that the pipeline is full, no ops are not required, and you can execute the program efficiently. And eventually you get the assembly code. So this is how typical front ends and back ends are organized, and these details could vary from a compiler to compiler. Okay. Before I go to the next slide, what do I have on the next slide? Maybe I'll pause here and take questions. Yeah, we'll talk about the structure of GNU toolchain, but any questions about typical compiler front end and back end? Does it make sense? Yeah. Some people will be talking about some back end phases in this workshop. Some people will talk about the analysis. In fact, nobody is going to talk about the front end, I think. So we will assume that the 300 abstract syntax tree or linear IR has been given, and then in this winter school we will see typically backend details. Okay, any questions? Any doubt? Okay, let's proceed. So how does GNU toolchain work? So you invoke this thing called GCC. You may have used this command line GCC, which takes a source program and produces a target program. Internally, it uses a compiler called CC1. CC stands for C compiler. If you have C++ program, there is CC1 plus or CC plus 1 or whatever that name is there. And then it includes a CPP, which stands for C preprocessor, and then it calls an assembler called AS, then it calls a linker called LD with an unfortunate name. LD stands for loader, but it's not a loader, it's a linker. This is an example of how a tool got named wrongly and stuck with that name. So LD is not a loader, it's a linker, but that's what the name is. Okay, and then it reads glibc and newlib. And this is where some of my teachers told me that the glibc version of glibc or C++, glibc, std, C++, there is a mismatch between how the program has been compiled on my laptop and how it's going to, what library does it expect on their laptop. It doesn't work. Okay, so this is the main part of the compiler. Assembler and linker is a separate part of the tool chain. Okay, and I will not go into the details of the architecture of GCC, but it's basically not just a compiler; it's a compiler generation framework. There's a language specific code, there's language and machine independent code, there's a machine dependent code generator, and there are these machine descriptions. And what GCC does is it produces this compiler as an output. It has a parser which reads the source program, through a scanner. And this is something called Gimplifier, which produces Gimpel representation. And there are these tree SSA optimization. Then there is expander, which essentially generates RTL. And then there is optimization on RTL. And there is this recognizer, which essentially gives us instructions. Color code matches. Everything in blue is machine independent generic code that is directly reused. Yellow is what is generated from the language part of the code. this part of the code is copied and this part of the code is generated. So we have to give input name and we have to give target name, and this framework at the development time generates the code which is then compiled, and that at the use time you read the generated compiler to take a source program and generate an assembly program. Okay, this is how GCC works. Okay. There is this LLVM tool chain which is again uses Clang, and it has Clang CC1, it has Clang -E which is pre-processing, there is a LLVM AS, there is a LLD which is a linker. So it's a similar structure. So these are the practical tools, compilers that people use. Okay, and then let's skip this part. How do you build a compiler? But an important part of the compiler is how was the first compiler written? Let's say you have a bare bone architecture, a new machine. How do you get a compiler running on it? That's called bootstrapping. How do you write the so I mean the natural question that should come to your mind is compilers are written in C and C++. Right? In order to compile this code of a compiler which is in C++, I need a C++ compiler. How did I get that C++ compiler? Maybe that was also written in C++. How did I get that C++ compiler? So this is a very interesting explanation that people have. So some people say in one of the mythologies that the earth is being held by a turtle. Earth is standing on a turtle. So somebody asked, where is that turtle standing? That turtle is standing on top of another turtle. Okay, very good. But where is this lower turtle standing? Then there is another turtle below it. Then people ask, so where is the third turtle standing? So the answer is, you don't understand, this turtle's all the way down. Right? There's a question, where is the lowest turtle standing? If the earth is standing on a turtle. So that's bootstrapping for a compiler. Let's look at this notion a bit. So we use this notation called T notation for a compiler, which is a modified version of what the standard OCT1 book says. So you have a C compiler. This is the input language, this is the output language, and this is the implementation or execution language. So I'm going to implement this compiler in this language, and I will execute this compiler in this language, and this is the name of the compiler called CC. So with this notation, let's see how is the compiler written when no compiler exists. That is bootstrapping. So maybe I come up with a new architecture, no compiler in that architecture. How do I even get the first compiler working on it? Right? I can't write that compiler in C++ because C++ compilation doesn't exist for that architecture. Right? So how do we do that? So the way typically it happens is that let's say you have the first compiler. The first thing that you do is you take an assembly program as the input and you produce a machine code as the output, and you write this in the machine language. Okay, that is easy to write because assembly instructions are very simple. Okay, you have an instruction of code and you have the operands. So you have to take this and encode it in the machine instruction. So that's very easy. So you can write it in machine language. Okay, now you have an assembler. Okay, once you have this assembler, so input language is assembly, implementation language is machine, and the output language is machine code. Once you have that, you have an assembler, you have implemented an assembler. Now you can design a language C0, which is a minimal language, simplest language. You can write the code for C0 in the assembly language. Okay, so your input language is now level 0C, minimal C. You have an assembler in which you have implemented a compiler that takes C0 and gives you machine language. You have lowest level compiler. Because of this, now you have a compiler for C0. Now you say, okay, now I have a compiler for C0. This compiler I have because I first wrote an assembler, right, which allowed me to write this smallest compiler. Now I have richer features. Now I can design a new language called C1. Write its compiler in C0. Now my input is C1. The compiler for C1 has been written in C0 because I have a compiler for C0. How do I have a compiler for C0? Because I wrote a compiler assembly. Right? So now I have a compiler from C1 to machine code. Going like this, we have level Cn and we have Cn minus 1 compiler. That gives us a compiler for language Cn level into machine code. And now I can write Cn code, Cn compiler in Cn language and generate a machine code. This is what is called bootstrapping a compiler. Okay. What GCC does is GCC says now you have a C compiler. Now you build a new compiler using that C compiler. That you get another C compiler. Okay. Now you compile C compiler. You have C source code. You compile it using the new compiler that you have generated. Get another version of the compiler. So now you have two compilers. One generated using the older compiler and one generated using the new compiler. And GCC requires these two binaries to be bit by bit same. If that is the case, then GCC assumes that you have built a new compiler successfully. Why would this be required? Because you have a compiler which doesn't have some optimization. Now you add a new optimization. So your language level doesn't change, but your compiler becomes richer. So this was an overview of the compiler structure. Now we want to look at scanning, parsing and semantic analysis, overview some more details of scanning, parsing and semantic analysis. And I would like to pause here and take questions. As I said, I am simply telling you stories at an abstract level. Whatever I have covered since 9:30 until solely 12 o'clock with a half an hour break. Whatever I have covered, 1 hour plus 1 hour, 2 hours, is something that I cover typically in 1, 2, 3, 4, 5, 6, 7 weeks in my class. And usually compile course. I've compressed it in short details. Now I will open up some more details. But before I go, I'd like to pause here. Please ask high-level questions, abstract questions. Yeah. Any questions? Okay. So let us say I hope you are able to see this. So I have some C compiler. So I have C source of GCC. Okay. I feed it through existing version of GCC, generated compiler, and I get a GCC compiler. Let me write it this way. And the output is a GCC compiler. This goes to GCC. Executable. Output is a GCC compiler. Does that make sense? Right? You have this C source. You're compiling it through GCC. What you're getting is a GCC compiler. Right? Now, this may be different from this GCC because maybe you also will just call it GCC prime. Okay, because maybe you have added a new optimizer, you changed some things, etc. But it still is the same compiler. It is more capability, but the language it accepts is still the same. Okay. Now I can feed this to GCC prime. Right? I have the same compiler. I can do the same source to my GCC prime as well. What will be the output? The output will be, let's call this GCC double prime, right? Possible? Make sense? No hand waving, no magic, just repeating the same step again because the input code is still remains same. Now, this is one piece of binary and this is another piece of binary. These two binaries should be bit by bit identical because both of them are compilations of the same C source. So I should get the same binaries. That is the idea. Is it? We stop at 2 or 3. Let me just check. Yeah. No, so 3, sorry. Then I go to another level. So I feed this and I get another GCC prime, triple prime, and these two have to be same because these two have been compiled using the compiler which has identical optimizations. This was compiled separately. So in build 1, so I do stage 3 build. So this is stage 1 output, stage 1 output, this is stage 2 output, and this is stage 3 output. Okay. Stage 1 was compiled by a different compiler. Okay. But stage 2 was produced. Stage 2 and stage 3 have been produced by a compiler representing the same source. And therefore, the output of GCC double prime and GCC triple prime must be identical. That is the meaning of bootstrapping in case of GCC. Okay. So that's the meaning of writing the same compiler in C. I mean, it seems confusing, but actually it's not. You just have to understand the concepts. Okay, so let's get on with introduction to scanning. So now I have to introduce scanning at a very high level. I have to introduce parsing at a very high level, and I have to introduce semantic analysis at a very high level. After that, we are ready to do the tutorial problems. I don't know how much we will cover by 12:30, but we'll break for lunch. So one of the promises that I have is not that I will cover everything in time, but I promise you that I'll break when it's time for break. If we want to stop at 12:30, we'll stop at 12:30. Even if you're not finished everything, we'll continue it after the lunch break. Okay. So let's begin with scanning. Okay. So here is an input program as you've seen it. This is just going in slightly some more details of what you've seen before. So here is an input program which essentially writes a sum of some numbers, some of first I numbers. Okay, and in this case, I less than 10, so first 10 numbers, right? That's a C program. Okay. What the compiler sees is something like this, where this indicates a blank character and this indicates a return character. Okay. A compiler, a scanner sees this as a sequence. So there is a letter M followed by letter A, followed by letter I, followed by letter N, then there is a blank. Then there is a round parenthesis opening, there is a closing round parenthesis, and there is a new line. Why is there a new line? Because I am giving a new line after this round parenthesis. Right? So that's what a compiler sees it. Okay. Sees as the input program, just a linear sequence. All the indentation, new line, etc. is for our visualization of the program. Compiler doesn't bother too much about it. Compiler simply says, I have a linear sequence of letters, lines to matter. Okay. Now the question is, how do you make the compiler see what you see? What you're seeing is this. What the compiler sees is this. Now these two have to match. Right? So how do you make the compiler see what you see? Okay. So what the compiler has to do is to break up this string into smallest meaningful units. So earlier we had here the green box is a sequence of characters. Now we have a So we have this token called name, which is name. We have another instance of this token called sum, which is an identifier. This is the name of the function. We have another instance of this sequence of characters, which the scanner knows is a keyword. It is not a variable name. The scanner knows that sum is a variable name and for is a keyword. These are strings representing two different tokens. How do you think scanner could be making this distinction? Yeah. Yes, exactly. The answer is that the scanner knows the list of keywords and the language has specified that these keywords can be used as variables. Right? So whenever scanner sees FOR, a sequence of FOR, the scanner will say it's a for keyword. But let me give you some interesting questions. Okay, now that we are at for, let's say I have the scanner sees this sequence FORM. What will scanner see? I can see a for keyword. Yeah. Yes. Okay. Is it always a blank character? Can it be something else? Okay. So the question is, the suggestion is that there are some special characters at which a token ends. Escape characters. So, for example, my input could be form plus IFABC. There's no space between them. What does scanner do now? So, do we have to say plus can end the token? You say that? Yes. But then I can write var plus plus. Yes. So we have to specify how the tokens are constructed. For each token category, we have to say linearly what can follow. And the scanner will try to read, scanner will speculate, maybe this is a variable name. And will keep reading until it finds things that can be a part of variable name. When it says no, no, next token can't be a part of variable name, then say, okay, now I have seen a string, I can't go any further. Then it checks, is the string same as one of the keywords that have been specified? If yes, the scanner will say, okay, I have seen a for keyword. Okay, this is possible only because the language says that keywords are reserved. They can't be used as variables, which may not be true for all languages. You know, here is a valid statement in Fortran, the first Fortran. Okay, what is a valid statement? If, okay, and you can write if EQ, or maybe if they are not operator, let's just use operator for equality. If equal to then I can write then equal to else, and then I can write else, and I can write else equal to then. Obviously, going for trouble. Keywords were not reserved, but most modern languages these days reserve keywords. You can imagine, how do you even scan and parse that program? You have to know that this instance of if, the first instance of if is a keyword, this is an identifier, this is an identifier, this is an identifier, or maybe actually they had a dense keyword as well. If equal to then equal to else equal to then. Right? This is an example of a bad design. So if you reserve the keywords, things become much better. So you try to write the statement in C and the compiler will say, no, I don't accept this. Okay. So we have to specify the patterns of the tokens, and then a scanner can subdivide the character stream into a sequence of tokens. Okay. So, okay. Going back, I held it down, upside down. Okay. So once you have done this tokens, you remove new lines and space characters. Parser doesn't need to know that I'm using a new line, right? You don't need a new line after every statement. You can break the statement in an arbitrary way. Okay, you don't need spaces. You can have one space, two space, or maybe space is not required. The way we wrote form plus 10, space is not required. Okay, so steps 1 and 2 are interlinked. So scanner keeps reading. Whenever the parser says, give me the next token, scanner keeps reading and says, okay, this is possibly this token until it can keep adding the same set of characters to that token class. Otherwise, it will change the token class. How does that happen? Very beautiful algorithms. Unfortunately, beyond the scope of this workshop. I usually spend 1 week or maybe 6 lectures on how scanning actually happens. Okay, so this is lexical analysis or scanning. Okay, now the next step is to group these tokens to form larger structure. Now you got the tokens, you got rid of the spaces and the new line characters, and then you create a parse tree that looks like this. Okay, you will observe these parse trees and abstract syntax trees for programs in the afternoon session. So the question is, why are we doing this in 2 steps? We are doing scanning, we are doing parsing. Why do we need a scanner and a parser separately? Can't we do both the things together? And the answer is yes, we can do both the things together. Why? What is the theoretical basis for this? The theoretical basis for this is, how many of you have heard of regular language and context-free languages? So if you run theory of computation, you have heard regular languages. Scanning requires a regular language. It's a linear sequence. You don't need the memory. You can describe the pattern using a regular expression, convert into a deterministic finite automaton, which is what is used by a scanner. Parsing requires a context-free language where you have to remember the token. Maybe you have to match the parentheses, you have to match the braces. So you push the tokens on a stack in order to match them. Now you know a fundamental result that every regular language is also a context-free language from Chomsky hierarchy. Every context-free language is not regular language, but every regular language is a context-free language. So scanning scanning can also be done along with parsing because regular language is also context-free languages. However, it is much easier to divide it in various phases. So there is a tool called Angular which combines the two. But it's much easier to, so it's a practical decision for simplicity, which says let me have scanning and parsing as two distinct stages. Theoretically, they need not be distinct. Okay. So, what is the lexical analysis or scanning? Lexical analysis is the operation of dividing the input program into a sequence of lexemes. Lexemes is the word which are strings representing token. Token is a category given to name given to a similar set of lexemes. For example, one of the tokens is an identifier. Now there are or variable. Now there are infinitely many variables, right? So count is one instance of this token, form is another instance of this token, average is another instance of these tokens. So what we do is so lexemes define the members of the class that a token represents. Okay, so you have to distinguish between lexemes. For example, I sum for 10 plus plus. These are all lexemes. Okay, and you have set of tokens. So a token is a name given to a set of all possible lexemes that have the same characteristics that can be described using the same pattern. So we have this token called identifier, which has lexemes I, sum, buffer, form, etc. You have this token category called integer constant, which is 1, 10, 20, infinitely many numbers. And you have this token category called addition operator, which is plus and minus. You could have multiplication operator, malloc, which is star and divide, etc. Okay, so we have to distinguish between when we talk about when we say we identify tokens in the program, that's a slightly loose statement. What we do is we identify lexemes representing token in the program. We pass on the token to a parser because parser knows that here I expect variable. Parser doesn't care whether the variable is form or format or whether it's buffer or whether it's average or whether it's called parser doesn't care. Parser simply says I have this token called identifier. Is a semantic analyzer which will bother about which lexeme it is. And why do you think semantic analyzer should bother about it? Any guesses? I said parser doesn't bother about which variable it is, but semantic analyzer bothers. Why? Yes. Some variable may be string, some variable may have type integer, some variable may have floating point. Parser doesn't care. Parser says, I am expecting a variable, but semantic analyzer needs to know which variable it is so that I can figure out what the type is. Right? So therefore, a semantic analyzer needs a lexeme, parser needs a token. Right? So what we do is we have a pointer to a symbol table entry of each token. So parser will create a parse tree with a pointer to the symbol table. Now semantic analyzer will say, okay, fine, I'm happy that you have found out a valid structure, but that's not enough. Does it have proper semantics? That's also an important thing to check. Okay, for example, if you talk about English statement, you're saying boy flies kite. You might write kite flies boy. That's semantically invalid, syntactically valid. So semantics therefore has to know it's a variable, fine, but which variable it is? What is its type? Right? So a scanner will do the following. Checks a variable, puts it in the symbol table, gives a pointer to the entry to the parser. The parser will create a structure. The parser will find out that this is actually a variable declaration. Then it will tell semantic analyzer, here is a variable declaration, please handle it. Now semantic analyzer knows in this variable declaration the first token has to be a type specifier. digits, and then we remove these characters, and then we create this structure. And why do we have these two steps? So we have to distinguish between lexemes and tokens. And what is the basis of grouping lexemes into tokens? Well, we can combine add-op and malloc. Why can't plus be a token in itself? These are all design decisions. I can have plus a token in itself, or I can have plus and minus in one token, and I have star and device in one token. Why do I want to distinguish between them? Because the precedences are different. In my language, the precedences are different. Okay. So lexemes which play similar role during syntax analysis are often grouped into a common token. Operators add-op and malloc have different roles. Malloc has a higher precedence than add-op. So therefore, I would like to have these as separate tokens. But nothing stops me from having plus as a separate token and minus as a separate token. In fact, if you see SCLP and show, we have plus op as a separate token and minus op as a separate token. It's a matter of design. Okay, each keyword plays a different role, so therefore it's a token by itself. Each punctuation symbol and each delimiter is a token by itself. So I want to distinguish between semicolon and equal to. Okay, comments are uniformly ignored. They are all grouped under the same token. All identifiers are grouped in a common token. So lexemes that are not passed to the later stages of compiler comments, they are ignored. White spaces, tabs, blanks, and new lines. They are just used to distinguish between things for a scanner, but later phases don't need them. These two are detected and ignored. Okay, so here is an example. You have lexeme 3. Its token is constant and its token value is 3. Lexeme is a string representing token. Now I have this lexeme A, which is an identifier, and its token value is either string A or a pointer to symbol table where A has been entered. There is a lexeme if, which is a keyword, a token if by itself, and there is no token value corresponding to it because that's a single token has a single lexeme. There are no multiple. So whenever we have a token whose set has multiple lexemes, we need token value. If we have a single instance, then we don't need a token value. Then we have assignment operator, we have relop, so we have name of relational operator and which operator it is. We have a semicolon, again one single token. I don't need the token value to distinguish between different tokens because I don't have different, I have exactly one lexeme for this token class. Right? So we'll talk about tokens, token values, and lexemes. Okay, so lexical analyzer detects the next lexeme, identifies, categorizes into right token, passes to the syntax analyzer the token name for further syntax analysis, the lexeme itself in some form, either it's a pointer or its value. So here are example tokens in Java. So identifiers are defined like this: a Java letter followed by 0 or more Java letters. Constants, there are these various kinds of constants. Then there are Boolean constants, there are character constants. This is how a language would define. Okay. For C, it could be something else. For C++, it could be something else. Okay. So for example, delimiters are, that's one token. Operators are these. Keywords are these. Okay. So how does one describe the lexemes that make up an identifier? So this varies. So for example, I can say identifier is a string of alphanumeric character, but the first character must be an alphabet. The first character cannot be a number. If I have first character, then I can have anything that follows. Now I can write a regular expression. I can describe the pattern by saying alphabet followed by digit, any number of digits. Okay. So or I can say string of alphanumeric characters in which the first character is alphabet, but it has a length at most 31. There are languages which say you can't have names larger than 31. Okay. Now you can regular expression would describe different tokens. Okay, and then a pattern is used to specify tokens precisely, and we build a recognizer from these specifications. So we have this scanner generator called Lex, to which the input is a sequence of regular expressions followed by the actions to be carried out by regular expression, and Lex will generate a C code which actually is a scanner. Right? So the place of scanner in a compiler organization. So as we saw before, we have a parser which invokes the scanner. This is generated from specifications and it returns the token to the parser. Parser does something, and here is the rest of the compiler. So this is the typical structure place of scanner in a compiler. Right? So we will take up the introduction to parsing and semantic analysis after the break. It's 12:30, so we can stop now. Any questions? Yeah. What is? The question is what is gimplified representation? Gimple is a representation which it's a very address code representation. Gimple stands for, it's spelled as GIMPLE. So gimplified is when you have program represented in Gimple is called gimplified representation, IR. So that's Gimple. Gimple came from Java. Java has a representation called Gimple, which is spelled with J, GIMPLE. Okay. That was inspired by an IR called Simple. So Java adopted it. They changed it to Gimple with GIMPLE. GCC adopted it. Everything in GCC has to begin with a G. So they changed J to G, and that's the name that they give. Right? So I think the first was simple and Gimple with a J, and then Gimple with a G. Computer scientists are very bad at good names. It shows lack of creativity. They do interesting work, but they can't find interesting names for the things. Yeah, answer the question. Yeah. And that's the reason why you should not consider all operators as a single token. Every precedence is hardcoded in a compiler in the form of a different category of operators. So typically we will have binary operator, unary operator. Within binary operator, you will have malloc or add-on. Okay. Or if you stay at binary operator, then you can't get the right levels. We will see when we talk about parsing. What kind of problems does it cause if you can't distinguish between different precedence levels? We'll see that example. But yes, it's important therefore not to have tokens of different categories given the same, different precedences given the same name. Makes things much harder. Okay. Any other question? Yeah, I know everyone is hungry, so you won't have any questions. If I keep pressing for more questions, I think a question will come up. When are you going to stop? We are hungry. So let me answer that question. We stop now and we meet after lunch. I hope you have sufficient food for your body and sufficient food for your mind. And when we come back, you would have sufficient energy to ask questions. We might talk about half an hour, maybe not more than that. There are very few things that we need to discuss. And then we will get into the practical work on your laptops. So we will break for lunch. Professor Vijaya will tell us how and where the lunch is. Yeah. Okay. Yeah. Yeah. So we have to be back by 2 and she will tell where to go.
work with